Hello guys, welcome back to my channel Gamma Die Gamma. So in the last video I believe we talked about differential operators. In this video let's move on with our discussion to multivariable integrals or multiple integrals. So let's get started. Okay, so just to give you a quick recap of single variable calculus, especially integral single variable calculus, is to point out that in single variable calculus we had, say, some function f of x like this, and then of course the x-axis. So what we did was we took this small infinitesimal segment on the x-axis and integrating f of x dx, we found the area under the curve. Okay, and that was basically this area for this dx, but then since we're integrating it, it's going to be all the area from whatever start point we had to whatever end point. So I'm not defining the upper and lower bounds, but you can clearly see it's whatever appropriate region we want it to be. Okay, so this discussion was explicitly for the area. Okay, what about the volume now? Well, what we can do, if you consider f of x to be like a length element, a length function, so I mean, it kind of makes sense, right? Because f of x gave you this height, this y height or whatever. So analogous to the previous case, we can write this as some area function of y dy, and this is actually a little more general, but just to give you some insight about what this exactly is, I'm gonna do a special case. Consider this square in the xz plane. So the area of that is just xz. So the area function, which is a function of y, is xz. Since x and z are both constants, yeah, so sorry for the pause, I was just pondering over which direction to give the label x and which to give z, because it has to follow the right hand rule. Okay, so your area function is this constant x times z, which is the area of this square section, and since this is integration dy and y is like pointing out of the page, the y direction is pointing out of the page, which means we're gonna have to stack. Now, I apologize for my bad drawing here, but we're gonna have to stack these squares on top of each other in the y direction. So assume this is like some stack here. So basically is this is the special case here. The volume is of a cuboid. Now, an interesting thing is this area of y looking at the previous case here, you can write this as another integral inside it, like a nested integral of some function now, which is a function of both x and y. Say dx dy. To be more general, this would be like a dA, but since we have this special case, I'm writing a dx dy. Okay, and one way of thinking about this would be, well, you have some region here. We can call this region R, that we are integrating over. So this is region R. What we're doing is we're taking some pieces in the x direction. So well, the x direction is this, so we're doing dx so f of xy is like in the, let's see, in another direction. It's not on this. Okay, a quick correction here. F of xy is like on this. It's on this other side. So if you integrate f of xy dx, well, in this case f of xy is just z. This is a constant function. But it could depend on y. It could depend on what stack we are on. So you're gonna get dx is like going this way. So you're gonna get stuff like this, and then dy. So again, we're gonna stack all of these. So first we keep the y constant because we're doing the inner integral first. This is like a nested loop. You complete your dx, then move on to the next stack of y, and then do your x again. So this is basically the same guy, the area of y dy integral, but instead it's showing you what happens with the area itself. So it's also showing you how the area is calculated. You can even go a step further and do like a triple integral over some, region O, and then you have dz dx dy. I mean, what you can do with from going from the second equality to the third is you can have your bounds go from, say, 0 to f of xy for the z part. The way that looks like is sort of like you already have like this like 3D region. Assume you have some function on top. So you're doing your dz first, so you're making these. You're first doing a dz, so you have like these length elements along with, after you're done with the z, then you start adding the x component or x dimension. to these lengths. So you basically have like a grid here. And then after that, then you proceed with your y integral, which will stack them up basically. This is a, I know it's a horrible drawing. I'm sorry about that. So I was trying to be as general as possible while also showing you the specific case of this cuboid. Okay, now let's look at this f of xy. Let's do like one solid example. Is x squared plus y squared. I love this function. It's a nice paraboloid over. So we need a region of integration over the region. Let's describe the region. So the region's like this. You have an xy plane. So it's a 2D region here, which is going to give us a volume because it's a 2D region now. Going from x is equal to 0 to, say, x is equal to a, and then y goes from 0 to where y is equal to x. So because we have this 45-degree angle subtending line here. So to set up this integral, and this is just to prove that you can have a function, you can have a variable in the upper and lower bounds of some nested integral. So for example here, for the z integral, these upper and lower bounds could have been functions of x and y. It was not necessary that they had to be constants. They were constants because this was a simple cuboid. But let me demonstrate that here. So when you set that integral up, x is going from 0 to a. So x is independent, x is outside. The inner guy, y, depends on x. So 0 to x. And then the function, of course, x squared plus y squared dy dx. So the inner integral with the inner differential and outer with the outer one. This we can evaluate 0 to a. So the concept of doing multiple integrals is similar to what we did for partial differentials, partial derivatives. When you're integrating with respect to y, treat x as the constant. I'm just skipping lots of steps here. And finally, you get a to the 4th over 3. If I'm not wrong, I could be wrong. And the deal with this, how does this look like? Well, it's a volume definitely, because you have a function integrated over some area. It's going to look a lot like, so the base is going to look like this shaded region here. And the top will look like this paraboloid that x squared plus y squared is. With a base that's kind of like this. I'm sorry, it's a bad drawing, but so you take some piece of this paraboloid which has the base of x squared of this triangle here. So it's kind of like this shaded region. I'm sorry for my drawing again. Okay, well, we know what uh, the basic idea of these multiple integrals, but uh, what do they look like in terms of Riemann sums? Is, say, if you have integral of x, f of x of y, dA. Being more general here now, this is nothing but the limit as delta xi goes to 0, delta yj goes to 0 of the sum over I and j. There's actually two sums, so I'm writing it as one. F of pij delta xi delta yj. This is what it looks like. It's a nested sum. That's why it makes sense that it is a nested integral, at least in this geometric sense that I tried to show you, of these making these grid lines. Okay, so by this logic, if you integrate some function over some area, you get a volume, where again the function represents the function, or should I say, be more specific and say a scalar field, always represents this length element. So length element times area will give you a volume. By a similar logic, a length element or a scalar field that takes points in R3 to R, integrated over volume element, which can be represented generally by d tau, some volume v. Since length element times volume is a 4-dimensional volume or a hypervolume. And of course, if f of xyz is 1, then it just becomes a volume, because then you just have where is it? This case here. Similarly, you could have even represented this as integral of 1 times dy dx over this appropriate area, this entire thing, this area S. So I hope this makes sense. I'm sorry if I confused you, but yeah, these things aren't exactly intuitive at first, but you can clearly break down triple integrals, volume integrals into these iterated integrals over segments, 2 segments, and then just putting layers on top of layers. Okay, so how about we take a vector field now. It takes points in R3 to points in R3. Something that looks like this, say f of x, y, z is equal to, say, f1, f2, f3. Now, assuming we have some path, some line, some curve, what we can do, the best thing to do is we can give it a direction, and then an even better thing to do is to parameterize this curve. So assume this is like the origin here. We can define a position vector from the origin to each point of the curve. Call this R vector. So R vector can be parameterized with a parameter t to be, say, x of t, some y of t, some z of t. This is a curve in 3 dimensions. So the dr, the sort of like the change, instantaneous change in the position vector, is going to look like something like this. At each point is going to be tangential to this curve. So dr is like the tangent vector. So dr just becomes, let's see, x prime of t, y prime of t, z prime of t, dt. So this is because of the chain rule. And say t, parameter t, is in this range of t0 and t1. So this is how we parameterize this path. So let's take a line integral. By that I mean, if this path, call this gamma, in this direction. Direction is important because that's what determines whether our integral is going to be positive or negative. What direction is positive, what direction is negative. Integral over gamma f dotted with this tangent vector. Okay, we can expand this out since we have a parameterization. This becomes integral from t0 to t1 f of, now plug in the parameterization. So x, so the x, y, z of f will be x of t, y of t, and z of t. Dot x prime of t, y prime of t, z prime of t with a dt. And it makes sense, right? A dt, and then upper and lower bounds are functions, are values of t. Okay, so this is what a line integral is. Let me just write that in another color. This is what a line integral is. Okay. So what is the physical intuition behind this? So you have some curve, and the vector field f is going to be this really big spread out vector field all over the place. It's not going to be just on this curve or just in the plane of the curve. It's going to be in all of R3 because this is a function from R3 to R3. So it's going to be all over the place. So when we plug in these parameters, these parameterized values, or this displacement vector in for the arguments of f, what we're doing is that we're saying that we only care about the values of the vector field that are between these two endpoints of the curve. So fine, whatever. We still have lots of values here, many vectors. So which ones do we even pick? Well, that's what this dot product does. It says pick only those vectors that are parallel to these tangent vectors of this curve. So when you do a dot product, you basically project all the vectors that are in this range along the tangent vectors at that point. So you get like these projections everywhere. This is horrible drawing, but hope you see projecting them. And then integrate those projection values, which will be scalars now, with respect to t along this curve. So that's the idea of this. So we care about the being in the direction of the curve, being in the direction given by the tangent vectors. So we care about being parallel to that direction. This is sort of like the analog of a directional derivative. This is a sort of a directional integral, in this case a line integral, because you just have one line. For a directional derivative we had one direction given by a vector. Okay, now an example of this, because examples are really important, of a line integral in applied mathematics or physics is work. The definition of work is force, which is a vector field, dotted with the tangent vector of a path along which you're moving. So assuming you have some object and you're moving it in some path, and there's this object is under the influence of this force free field or whatever. So the work done from moving from this point A to point B along this path in this direction is given by this, where we have to select the right parameterization, of course. But again, you clearly see you care about what direction you're going in. If the force is like completely parallel to the tangent vector at one point, well, that's when this dot product is going to be maximum. So it wants the force vector to be as much parallel to the tangent vector at each point as it can be. And this clearly coincides with the definition of work in physics. So this is one good example. Work done along a path. Okay, so this was line integrals. We integrated along a line or whatever. Now let's look at surface integrals, when we actually integrate over a surface. Okay, see you on a fresh page. Okay, so now let's take some surface. Again, I'm making it weird because I want to make this idea as general as possible. So this is like some fancy distorted cuboid. Again, apologize for the drawing. Okay, now what you want to do, again, F is as before, vector field from R3 to R3. So let's talk about this surface S. F, definition of the surface integral is F dotted with this area element vector. Now what is this area element vector? Before, for the line integral, we had a tangent vector. Can we take a tangent here? Well, the answer is no, because if you choose a tangent in like this arbitrary direction, you can also choose a tangent in this direction. So there's no one clear choice of what tangent vectors to take, because if you take a tangent vector, say along this left side here, you keep going, you keep going, you keep going, you end up with a left side, but you have so many other directions here, not just left and right. In a line integral, we had that one line. Here there's no clear choice of direction. So what we do, for the sake of orientation, and this is a topic of independent study in mathematics, I think, how to orient surface, how to orient manifolds. So that orientation criteria that we develop there, say that we need a vector that's perpendicular to the surface, because only that vector can help us with this kind of integral. So this dA vector is just dA, which is area differential, dotted with this unit normal vector, which I'm showing with these arrows on this surface. Okay, so what's the physical intuition behind this? Is, well, if you have this surface and it's surrounded by this big vector field, which is f vector, you want to find vectors or projections of this vector field that are perpendicular to the each face of this surface. So in this case here, we want vectors that are parallel to this normal vector. So we take projections similar to what we did for the line integrals. There we took projections when we projected the vector field vectors onto the tangent vector. Here we're projecting it onto this normal vector. Now again, the orientation is important, because if two faces are exactly equal, like say if you have a cube, well, two faces, opposite faces, say like this face and that face, will have exactly equal and opposite area vectors. So you actually care about the sign here. So this is an important discussion, because that only shows you how important orientation is. For if we'd chosen like tangent vectors, it would have been really hard to know what direction we are going in and what orientations are positive, what orientations are negative. In this case, we clearly know what areas are positive, or at least what area element vectors are positive and which ones are negative. So we can split up our integral that way, with positives on one side, negatives on the other. Because again, if you're defining your x-axis this way, y-axis that way, and z-axis upwards, you know that this is in the negative x direction, this is in the positive x direction. So that helps us with our orientation. So one example of this, we had a work for line integral. Surface integral, we have flux, say electric flux for now. So the amount of electric field lines crossing a surface S, that measure is called the electric flux. And this is of course extremely important in electrostatics and dynamics. I forgot to mention, just like the line integral, you can also parameterize a surface, but you need to use two variables, say u and v, over some range. And then you'll have instead of dA, you'll have du dv over the appropriate upper and lower bounds. And of course you do the chain rule as before, but you respect orientation as I explained here. Okay, so moving on to what else remains is actually volume integrals. So let me just change my color here. Okay, so volume integrals are actually not that hard. They're way simpler. If I think of them that way, they're way simpler than surface integrals, because you don't do it on vector fields anymore, you do it on scalar fields. So assume this is a scalar field. It takes points in R3 to points in R. Well, then the volume integral, you define it simply as this: triple integral over some region V of this scalar field d tau, where d tau is your differential element. And it can be dx, dy, dz depending on what parameterizations you choose. I'm just being more general here. So as I said, this is a scalar field, and it's simple. It's as we discussed before, it's going to give you a hypervolume. So it's hard to visualize, but if you have some volume like this, you attach weights to different parts of this volume and you get like this quantity that could geometrically be interpreted as a hyper volume, four-dimensional volume. One reason why we don't have a vector field for the volume integral is that that's the way orientation is defined on R3. Well, curves in R3 are oriented, surfaces in R3 are oriented, but volumes in R3, there's you can't really orient them in some way because those rules would be different. Like R3, a volume, a 3D surface would be treated as a 2D surface on R4, for example. So you could orient that on R4, but in R3 you can't really. Another reason, so one reason is that just orient the way orientation works mathematically, and it's a big thing, so I urge you to look into it if you're interested. Another reason is if you think about integrating differential forms on manifolds, well, the 3 form on R3 works similar to a 0 form on R3. That's just because it's R3, there's certain symmetries associated with this, just how things work here. So it's because of that. So you can treat a function that can be triple integrated similar to a simple function that is like just a simple function that that is not integrated at all. So it's like that. One example of a triple integral, volume integral, is mass. Well, a mass can be expressed as a triple integral of a density function of x, y, z, for example, d tau, because the density may not be uniform. It can be non-uniform in terms of this function. So you just integrate it over the volume. Each point gets a say on what the density is, and you integrate it, and you get accumulated density on each volume element, and that is the total mass.